So welcome to the first session of this afternoon. It will be about ciphers for FHE and ZK. So will be three papers presented, two on designs and one on cryptanalysis. And the first paper is a new scheme called FRAST, so TFHE-friendly cipher based on random S boxes. And it will be presented by Jinshal Ha.
Okay, good afternoon, everyone. I am Jinchal Ha, and I will present our new TFH-friendly cipher, FRAST. This is joint work with Mingyu Cho, Woo-Hyuk Jung, Ju-Young Lee, Eun-Gyo and Min-Chul Son. For the beginning, I will briefly introduce about the homomorphic encryption and TFH scheme and trend ciphering. Homomorphic encryption is an encryption scheme that enables operation over encrypted data without decrypting them. So we can protect data when they are actually used, not only for when they are stored or transmitted. And currently, most of the HE schemes used now is based on LW encryption, which has a noise inside the ciphertext. And during the homomorphic operation, this internal noise grows, and if the noise flood over some threshold and corrupts into the message space, operation named bootstrapping is proposed to refresh the noise. So this bootstrapping is one of the key operations in HE schemes. And TFH scheme, one of the HE scheme that supports fast bootstrapping along with homomorphic lookup table operation. So each LW ciphertext encrypts a bitwise input or a small integer of about 4-bit size. And nevertheless, of these useful functionalities of HE schemes, there is one inherent problem called ciphertext expansion. That is, to separate the message from the noise inside the ciphertext, the ciphertext size should be larger than the message size. So this basically increases the amount of data to be transferred. So transciphering is one of the methods to handle the ciphertext expansion by combining HE schemes and symmetric key ciphers. This figure describes the basic workflow of transciphering framework. And for client side, the client encrypts its message using stream cipher and send the encrypted message to the server side without ciphertext expansion. And then for the server side to so the server basically do the decryption circuit of stream cipher homomorphically. So it benefits the client side at the cost of additional operation on the server side. So to do this additional operation efficiently, there were basically two kinds of approaches. First one is for this purpose, designing a TFH-friendly cipher. The Elizabeth cipher is the first proposed TFH-friendly cipher, and after it was broken, its variants are proposed to mitigate the attack. And the second approach is proposing an efficient evaluation method of existing stream cipher. For example, there was a work of evaluating Cravium, which is a variant of Trivium stream cipher to support 128-bit security. Our work basically followed the first approach. So we designed a new TFH-friendly cipher named Frost, and we obtained a higher throughput than previous works. And for reference, after our work proposed, there is a new stream cipher named Transistor, which has better performance than ours. So before going to the details of Frost, I will give very short and brief TFH background. There are many ciphertext types are used in the TFH scheme. Basically, the LWE ciphertext is used to encrypt an integer message. And its generalized variant, called GLWE, is used to encrypt integer coefficient polynomial. And it is usually used to encrypt a table to evaluate during the homomorphic LUT operation. And one of the important ciphertext type is GGSW, which stands for Generalized GSW ciphertext. It's a special type of ciphertext that supports homomorphic multiplication with linear noise growth. So it is usually used to evaluate controlled mux gate, or CMUX gate in short, which can select one of the GLW ciphertext without knowing the selection bit B. This is the basic idea of evaluating an LUT operation inside the TFHE scheme. The table we want to evaluate, which is denoted small fx, is encoded into a polynomial, and it is encrypted as a GLW ciphertext. And what we want to do here is moving the value we want, denoted fm, into the coefficient side of the GLW ciphertext. To do so, we multiply x to the minus m to the GLW ciphertext. If we have GGSW ciphertext of each bit of the message m, then we can do it using a small number of CMUX operations. But if m is given in an LW ciphertext, which is the case of PBS operation, then we need hundreds of CMUX operations. This basically rotates the table inside the ciphertext, so it is called blind rotation. And after the blind rotation, we can extract the coefficient component into an LW ciphertext with almost no cost. Now let's move on to our new cipher, Prast. There are two design rationales of designing our cipher. First, to make the round function of Prast TFH friendly, we use the structure of generalized Feistel network. And combined with our new evaluation method called double blind rotation, we could evaluate multiple S-boxes at the cost of a single S-box call. But this efficiency-oriented structure make our Prast vulnerable, so it might lead to an unknown attacks. So to mitigate these issues, we opt the circuit randomization strategy on S-boxes of Prast. For designing HE-friendly ciphers, it is common to randomize its linear layer using the nonce or IB value to enhance its security without increasing the round numbers or without using homomorphic operation overhead. Because TFH supports homomorphic lookup table, we can randomize these S boxes. So this is the structure of Prast round function. The internal state is 120 bit, and it is divided into 32 branches of 4 bit each. And the addition operation performed over integer modulo 16 to match with the LWE addition. The round keys are generated from the master key of 256 bit by linearly expanding it. And the most important key feature is that the first branch, denoted by x1, is used as a common input to the same S boxes with different round keys added. And the S box outputs updates the other branches, and then the sum of the updated branches again become an input to the last S box, and it updates the first branch. And according to the type of S boxes, the round functions are divided into two types. First one is random rounds, which generates its S box randomly from the XOF outputs. For fixed round, we choose a fixed S boxes, fixed X box, which is chosen to have a good algebraic property. Under this structure, we evaluate the first 31 S boxes of Prast efficiently by using double blind rotation. The idea is separating the rotation in two steps. First rotation by X1 and second rotation by the round key. Because the first rotation output can be shared for all the S-box output, we can do the first rotation only once, and the second rotation we do it for each round keys. For the first rotation, the X1 value are given as an LW ciphertext, so it requires one PBS operation. But for the second rotation, to do it efficiently, the client sends the GGSW ciphertext of all the round keys. Because the round key is fixed for each master key, the number of round keys is limited, and client send it to the server in the setup phase. The round function of Prost follows the block cipher structure, but most importantly, because we use Prost in the train ciphering framework, we will use it as a stream cipher with the following mode. It looks like the counter mode, but the difference is the input is fixed as a known public constant, and the circuit is changed for each keystream block by the XOF outputs. It looks like the encryption mode of the last cipher. There are total 40 rounds, which consist of 32 random rounds and 8 fixed rounds. And the number of keystream block for each nonce is limited to 2 to the 60 to prevent nonce collision when nonce is generated randomly. Now we briefly summarize our security analysis. Based on the randomized S boxes and the encryption mode of the Prost, which use the fixed constant input, typical chosen plain text attack is not possible. For example, to do differential attacks or integral attacks, the attacker needs some controlled input to a fixed circuit. And it was hard to analyze these kinds of attacks on the full round of Prost because two types of round function have two different characteristics. So we analyze linear attacks only using the random rounds of Prost, and we analyze algebraic attack different encryption circuit for each data. Instead, we consider the following three possible attack models. First one is applying non-zero mask to the XOF outputs, which determine the random S box of Prost. You can think it as considering the XOF output as an additional input of fixed Prost circuit. And second one is considering some equivalent S boxes, which means that although the S box, the exact specification of S box are different, they behave equivalently on certain linear mask. For example, under modulo 16, the linear mask of 8 means only the parity bit is considered. So although there are two different S boxes, they can behave same under the linear mask of 8. Last one is considering the weak S box, which may have some linear representation that can pass the linear tray with probability 1. So considering those kind of attacks, we find that 22 random rounds can prevent these kind of attacks, but we put 32 random rounds to prevent some unknown attacks, such as considering key guessing. Next one is algebraic attack, but as Elizabeth is, Prost has no polynomial representation over integer modulo 16. So similarly, we consider the XOR variant of Prost. The mainly considered attacks are trivial linearization and XL attacks. And we found that 6 rounds can prevent this kind of attacks, but we put 8 fixed rounds with 2 marginal rounds. Finally, we evaluated our cipher Prost using FHE and compared the performance with previous works. For the previous works, we estimate their performance by measuring their building blocks. For example, measuring the PBS time under their parameters and multiply it by the number of PBS required for those ciphers. So you can find that our cipher Prost has higher latency for generating one keystream block, but its performance is higher because the keystream block size is much larger than the other ciphers. In this case, we believe that having a higher throughput is more important because when we use transciphering, the size of data we transfer is at least 120 bit. And the setup time of Prost was about 25 seconds when our paper was when submit our work, but recently we improved it to about 2.6 seconds by applying some FFT optimization recently proposed. Thank you for listening, and feel free to give any questions. Thank you.
I have one small question. So you say you use a random S-box. Is it required to be a permutation or not?
For random round, it is not permutation because we use the
So at
legacy click S-box, which might not be a permutation.
So
But for
you mean-
fixed round, it is permutation.
so you mean at the setup phase, so you don't reject some bad S-boxes, right?
Pardon?
I mean, at the setting up phase, you will not do rejection. Like,
Yeah, no rejection.
okay, thank you very much.
We only sample 8 random elements and expand it legacy click.
Any other question? Just maybe a small question. So how did you choose a number of 40 rounds? Can you explain?
Yeah, it was chosen by 32 random rounds and 8 fixed rounds. Each type of round were determined independently. And 32 random rounds consider the linear attacks, and 8 fixed rounds considers the algebraic attack.
Thanks. So let's thank the speaker again.